In this video, we are going to look at questions on carbohydrates, and these questions are coming from Tutor Sheet 4, Lusaka Apex Medical University. Okay, so we have 5 questions in this tutorial sheet. We are going to solve them one by one. So we start with question 1 there. Okay, so question 1, they're saying, with the aid of a flowchart, explain the different types of isomers monosaccharides can exhibit. Okay, so I've already drawn the flowchart here, so I'll explain whatever you can see here. Okay, so the first type of isomerism that monosaccharide can exhibit is what we call as the structural isomers. And then they can also exhibit stereoisomers, and then they can also exhibit optical isomers. Okay, so now what are the structural isomers? So the structural isomers, these are just isomers that have the same molecular formula but different structural arrangement. So they are subdivided into what we call as the chain isomers and the functional what? Isomers. So the chain isomers, these are isomers that differ in the arrangement of the what? Of the carbon chain. And then the functional isomers, these are isomers that differ in the position of the functional group. So a good example of functional isomers is the aldose functional group in the glucose and the ketose functional group in the what? The fructose. All right, and then we also have stereoisomers here, okay? So these stereoisomers are just isomers that have the same structural formula but differ in the spatial arrangement of the what? Of the atoms. So they are subdivided into enantiomers and diastromers. So these enantiomers are just mirror image isomers that are non-superimposable, okay, with each other. Meaning you cannot put one molecule on top of the other and it will align perfectly that, okay? So the perfect alignment does not happen, okay? So that's what we mean by mirror image isomers that are non-superimposable, okay? And then the diastromers here, these are just isomers that are not mirror images of each other, and they differ at more than one what? Chiral carbon. Okay. And then these monosaccharides also exhibit what we call as optical isomers. Okay. So these optical isomers, they come about um, when the plane polarized light is rotated either to the right or to the what? To the left. So when these optical isomers rotate the polarized light to the right, we form an isomer that we call as dextrorotatory. Or in short form, we just say the deform isomer. And then when they rotate the plane polarized light to the left, we form what we call as what? Revorotatory. Or in short form, we just say the L isomer. Okay, so these here are the main types of isomers that monosaccharides can what? Exhibit. Okay, and then we go to question 2 now. So question 2, they are saying, okay, question 2, they are saying, in the Fisher projection formula, what do the vertical and the horizontal line represent? Okay, so a Fisher projection is something that will be in this form. So you can have H2OH there, okay, and then maybe double bonded to oxygen there, and then you have these bonds where I can have H there, OH, and then H, and then OH, and then even here I can have CH2OH. Okay, so whenever you see something like this is the Fisher projection. Okay, so what do these vertical lines represent? This line here, which is vertical like that, what does it represent? And also, what do these horizontal line here represent? Okay, so I'll start with the horizontal lines. Horizontal. Okay, so these horizontal lines, okay, they represent bonds coming towards the observer. Okay, they represent bonds coming towards the what? The observer. Okay, or we can say they represent the bonds that point out of the plane of the page. Okay, so they are coming towards you, they observe, they are pointing out of the plane of the what? Of the page. And then the vertical lines, okay, the vertical lines represent bonds going away from the observer. Okay, away from the observer. So meaning the bonds, okay, that are pointing into the plane of the page. Okay, so these are bonds pointing into the plane of the page, or you can simply say bonds going away from the what? From the observer. So that's what the vertical and the horizontal lines mean. And then B there, we have if an atom or group of atoms is shown on the left in the Fisher projection, how would such an atom or group be shown in the Haworth projection? Okay, so the Haworth projection is just this form where you have a ring like that. Okay, so this is the Haworth projection. So where the atom is going to be shown, or the group of atom is going to shown, okay, depends on the form or the conformation of the molecule that you have. So if you have D sugars, okay, the representation of those atoms on the left is going to be different from when you have what? L sugars. Okay. So if you have D sugars in the Fisher projection like that, the atoms that are being represented on the left here, okay, when you draw them in the ring, that is a D sugar, they are going to be above. Okay. They're going to be above the plane or above in the ring. Okay. Or above in the ring. Okay, so what I mean is, for example, if this is carbon number 3, right? Okay, so we have carbon number 1, 2, and then 3 is there. So this carbon number 3 is connected to this OH on the left and then H on the right. So if you have OH on the left, it means there is going to be above there. So you're going to write your OH above. And then if you have H on the right, okay, as long as it's a D sugar, it means it has to be below the ring like that. Okay. Yes. Okay. And then if you have L sugars, okay, it means the atoms that have been represented on the left here, they need to be below the ring. Okay, below the ring. And then the atoms or group of atoms that are on the right, when you're dealing with the L sugars, they should be what? Above the ring or above the plane. Okay, so that's uh, how you represent those atoms. Okay, so always make sure you know the form that they are talking about. Okay, if it is the D sugar, okay, then those on the left will be above, those on the right will be below. And then if it is the L sugars or the L conformation, it means that those on the left will be above the ring, and then those on the right will be what? Below. All right, so that's that on question 2. Let's now look at question 3. Okay, so question 3, they're saying draw the Haworth projection, okay, of the following monosaccharides, making sure that you illustrate or show the process of what? Cyclization. Okay, so here we have galactose and then we have hexerulose here. Okay, so before you draw the Haworth projection, you have to know the conformation of this molecule that you've been given or of this sugar that you've been given. So in most cases, they use the D conformation. So here we are going to use D-galactose. Okay, we're going to use D-galactose, and even here we're going to use what? D-hexerulose, like that. Okay, so we're going to get this D-galactose, and then we are going to turn it into a ring from its Fisher projection. Okay, so we have about 4 steps that we need to follow whenever we are drawing structures from the Fisher projection into the ring form. Okay, so the ring form is what we are referring to as the what? The Haworth projection. Okay, so The first step, okay, is to draw the Fisher projection. So I'll just write FP. So draw the Fisher projection and number the carbons. Okay. After that, step 2, you are going to rotate. Okay, you are going to rotate or turn your molecule 90 degrees clockwise. Okay. And then after that, when you turn it 90 degrees clockwise, okay, if it is a sugar or a molecule that has 6 carbon chains, okay, it means you have to take this additional step. You have to rotate. You have to rotate the covalent bonds or the covalent bonds, okay, at carbon number 5. So if it has what? 6 carbons. If that molecule has 6 carbons like galactose, we are going to rotate the bonds at carbon 5. Okay, we are going to rotate them what? Clockwise like that. Okay, and then the last step now is just to form the ring. Okay, so these are the steps that we are going to follow. So we are going to show the whole process of cyclization there. So we start with the galactose, the D-galactose there. Okay, so the first step is to draw its Fisher projection and then number the carbons. So let's come here and then begin our drawing. Okay, so we have this, we want to draw the structure of D-galactose. Okay, so D-galactose has the following structure in the Fisher projection. It will have C, which is connected to O, and then H, okay, and then connected to another C, which is connected to OH, and then H, okay, another C, which is connected to H, and then OH, another C, which is also connected to H on the right, OH on the left, and then another C connected to OH, and then we have H there, and then another C, which is connected to 2 hydrogens and an OH like that. Okay, so this here is the Fisher projection for what? For D-galactose. So we have drawn the Fisher projection. The next step is to number these. So we have 1, 2, 3, 4, 5, and then 6. Okay, so now the next step that you have to do is to rotate this molecule, okay, 90 degrees clockwise. So meaning that whatever you have on your right here, it is going to go down. And then whatever you have on the left here is going to go up. So what I mean is this. Let me highlight this molecule that I drew. Okay. So if I highlight this molecule that I drew, okay, let me just erase this part. So if I get this molecule that I do, we said we have to turn this molecule 90 degrees clockwise. So notice what will happen to it when I turn it 90 degrees. It will turn like that. So you see how it's going to appear, right? Okay. So now we are going to draw it in that form. Okay, so I'll just showing you what it happens when we rotate it 90 degrees clockwise. So it turns like that. So it means let's now draw it. Okay, let's draw a separate drawing. So he said this one here rotates 90 degrees clockwise. So we saw what it formed there. Okay, we saw what it formed. So what is going to happen is that I'm going to have C bonded to another C, 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 C. So when it rotates like that, 90 degrees clockwise, this carbon 6 is the one that is going to be here. Okay, and then there you're going to have your carbon 5, then there are 4, and then 3, 2, and then we should add also the carbon 1 there. Okay, so that will be our carbon what? 1. So this carbon 6, notice what it is bonded to. H2OH. So I'm going to write H2 there and then OH. So that's the carbon 6 there. Maybe I should write it in a different color. Okay, so let me say 2H and then O should be H2, okay, and then O, H like that. Okay, so this is what is bonded to the carbon 6. And then to the carbon 5, okay, we have OH on the right and then H on the left. So it means the OH there comes down here. And then we have the H above. On carbon number 4, we have the H on the left. The H on the right, so it comes down. And then up there, we're going to have the what? The OH. Okay, on carbon number 3, we have the HCO down and then the OH on top. Then carbon number 2, which is this part here, we have the OH down and then the H above like that. Okay, and then now we have this carbon number 1. So this carbon number 1 is bonded to oxygen and then to the what? To the hydrogen like that. Okay, so this is the what? The second steps. Okay, the second step, I mean. Okay, so the first step was to draw the Fisher projection and number it. And then second step is to rotate it 90 degrees clockwise. We are going to get this molecule here that we can see. Okay, and then from there now, we said if your sugar has 6 carbons, you have to do a bond rotation, okay, at carbon number 5. So this here is our carbon number 5, this guy here. So what is going to happen here is that these bonds, this H, this OH, and then this whole group here is going to rotate in a clockwise direction. So this H will come where the OH is, this OH will go where this group is, and then this group will go where the H is. Okay, so what are we going to form there when that bond formation occurs? Okay, we are going to form something like this. So I'm going to have C, and then C, 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 and then C. Okay, so this is my carbon 5 here. So this carbon 5, what has happened is that this H has come now below. This OH has gone on the left side, and then this whole thing here, the CH2OH has gone up, and then the rest is just the same. Okay, the rest is just the same. So here I'm going to write H, and then OH, H, and then OH, and then here we also have OH, and then H. Okay, and then we have H there, double bonded, this carbon double bonded to oxygen like that. Okay, so we've done the bond rotation there, which was the third step. So after we do the bond rotation now, we have to go ahead and form the ring. Okay, we have to go ahead and form the what? The ring. So how are we going to form the ring? So I'm going to say, okay, so I'm going to come here like that. Okay, so the ring formation, let's write ring formation there. Okay, so what will happen is that there will be a reaction between the oxygen of this OH and this carbon number 1. Okay, so it means this is carbon number 1, 2, 3, 4, 5, and then we have 6 there. So this OH attached to the carbon number 5 and this carbon number 1, they're going to undergo a reaction. Okay, they're going to undergo a reaction to form the ring. So it means this carbon 3 and 2, they are not part of the reaction. Okay, so the carbon 2 and 3, they will remain intact there. So I'm going to show them like that. I'm going to show them like this. What's happening? Okay, I'm going to show them like this. So I'm going to say, this is my carbon number 2. This is my carbon number 3. And then from my carbon number 3, we have this carbon number 4. So this carbon number 4 is going to go like that. Okay, I'm going to have my carbon number 4 there. Okay, and then from the carbon number 4, I'm going to attach the carbon number 5 somewhere there. Okay, so it's going to go there. So we have your carbon number 5 there. And then from this carbon number 2, I have my carbon number 1 there. Okay, so this carbon number 1 is double bonded to the oxygen, then bonded to the hydrogen. And then this carbon number 5, remember this is the carbon number 5 here. Okay, the H here comes down there. And then this group here remains on top. Okay, and then this OH here comes and bonds this side. So I'm going to write O and then bond it to the H like that. Okay, so that's what we have. And then we can put the OH and the H on these other atoms and on these other carbons, I mean. So on the carbon number 2 here, we have OH down like that, and then H. Then carbon number 3, we have H down and then OH. Carbon number 4, we had H down and then OH. Okay, so that is what we have, right? Okay, so now a reaction is going to occur between this oxygen that you can see here and this carbon here. So why is that reaction going to occur? Okay, this oxygen, the way it is here, okay, it has 2 lone pairs of electrons like that. Even this one here, it also has 2 lone pairs of electrons like that. Let me draw it properly. It also has 2 lone pairs of electrons like that. Okay, so these 2 lone pairs on this oxygen, they are going to cause it to have a partially negative charge. So we're going to put partially negative charge there. Okay, and then this carbon here, since it's bonded to an oxygen, the oxygen is more electronegative than this carbon. Okay, so it's like we have a partially negative charge on this oxygen as well, and then there will be a partially positive charge on this what? Carbon. Okay, so that's why the reaction here will occur. So what will happen is that these 2 electrons here, okay, they are going to attack this partially positive what? Carbon. So when they do that, they're going to form a bond between this oxygen and this carbon here. Okay, so these 2 electrons here are going to go into a bond, and that they're just going to turn into a line like that. Okay, so when that happens, it means this carbon here. Remember, carbon can have a maximum of what? 4 bonds like that. So if this oxygen attaches to this carbon, it means this carbon has 1, 2, 3, 4, 5 bonds. So what will happen? One of these bonds here, where the carbon is double bonded to the oxygen, one of these bonds here is going to be pushed to go into the oxygen as a lone pair. Okay, so one of these lines is going to disappear there, and it's going to become a lone pair on this oxygen like that. Okay, so it means now what we have is this. So I'm going to erase the part that I've undergone the reaction. So this positive charge goes, okay, and then what we have is we have the carbon here, which is bonded to the what? To the oxygen like that. So since this oxygen here has lost one of its lone pair, okay, it has lost one of its lone pair, it's going to become positively charged. And then here, what will happen to this oxygen that has gained an extra pair of electrons? Remember, this bond has gone. Okay, there's just now one line there because one of it has turned into this lone pair. So this oxygen here has received an additional lone pair. So what is going to happen to it? Okay, it's going to be negatively charged like that. Okay, so this is the situation that we have now. Okay, and then from there, what we are going to experience is, okay, this oxygen here is going to, since it's more electronegative than this hydrogen here, it's going to grab the electrons that are present in this carbon here to itself so that it becomes neutral again. So what will that cause? Okay, it means this bond will disappear, okay, and then the oxygen will gain 2 lone pairs of electrons like that. So if it has 2 lone pairs of electrons like that, it means this positive charge will no longer be there, okay, because it has sufficient electrons. So it means that positive charge is now going to be on this hydrogen here. Why? Because this hydrogen has lost the 2 electrons that it was bonded to the oxygen like that. Okay, it has lost them. So it has a deficiency of what? It has a deficiency of the electrons. So it becomes positively charged like that. So when it becomes positively charged like that, it goes on and attacks this negatively charged what? Oxygen. Okay, so when that attack happens, it means that this hydrogen here is going to get one of these lone pairs here to form a bond with this what? OH. I mean with this O here to form the OH. So what will happen there is I'm going to erase one pair there, okay? And then I'm going to say that pair has gone and reacted with the hydrogen and it has become OH like that. So it means this OH plus is no longer there now in the solution. Okay, it's no longer there in the solution. It has formed OH there. Okay, so now what we have formed here, is the Haworth structure for the what? For the D galactose. Okay, so you can even erase these partial charges. You can even erase this. You cannot show these lone pairs of electrons like that. Okay, so the structure now that we have there is our what? D galactose, but in ring form or in Haworth structure. So what would be the name of this Haworth structure? So it depends on the position of the OH. Okay, so if the OH is down like that, okay, if the OH is down like that, we're going to say this is alpha D galactose. Okay, it's going to be alpha D galactose. But if the attack was from the bottom here, and then this OH maybe was here on top, okay, or above, and then here we are at the H like that, that there is going to form the beta D galactose. Okay, so two forms of the galactose can be formed. It can be alpha if the OH is down, or it can be beta if the what? The OH is up like that. But in our structure there that we found, our OH was down, so we are just going to get what? The alpha D galactose. So we have turned this Fisher projection into a Haworth what? Projection, or into a ring projection. So this is what we have. So this here is the final answer, and I've explained all the steps that you need to take in order to find that structure. All right. So now let's look at the other one, which was the hexellulose. So we said we are also going to use the D hexellulose there to show the cyclization. Okay. All right. So when we have the D hexellulose, so D hexellulose. So this D hexellulose, its Fisher projection is just this one. So we have CH2OH, okay, and then this is bonded to another carbon, which is bonded to oxygen, and then we have another carbon bonded to H, and then bonded to OH, and then another carbon bonded to OH on the right, and then H on the left, then another carbon that is bonded to H2OH like that. So this is the first step. We have to draw the Fisher projection, and then we have to number this. So this is 1, 2, 3, and then you have 4, and then 5. So notice that this hexellulose has only 5 carbons. So there's no need for you to do the bond rotation that we did in the previous question. Okay, so the first step always is to rotate this guy 90 degrees clockwise. Okay, we have to rotate this guy 90 degrees clockwise. So if we do that, this is what is going to happen to this molecule. If we rotate it 90 degrees clockwise, it's going to form something like that. Okay, so now let's draw this on the separate diagram here. So we are going to say when it rotates, it just forms a C. Okay, let me get the pen. So when it rotates, just forms C, which will be the C5 here, bonded to C4, bonded to C3, bonded to C2, bonded to C1. Okay, so on the C5 here, we only have this group here. So I'm going to say H2 or H like that. This is the C5, this is 4, this is 3, this is 2, and then this is 1. And then on carbon number 4, what do we have? We have the OH down, and then the H above. On carbon number 3, we have H down, OH above. On carbon number 2, we have the oxygen down there because it's on the right here. And then on carbon number 1, okay, we have H2OH. So that would be H2OH like that. So this is the molecule that we get when we rotate this D hexellulose, okay, 90 degrees clockwise like that. All right. So once we do that, since here there is no need for you to do the bond formation, the bond rotation there on carbon number 5, you just go straight and start forming the what? The ring. So what you are going to get is this. So we're going to say ring formation here. So ring formation. Okay, so what we are going to form is something like this. So remember, here what is going to take a part in the reaction to form the ring will be this OH on carbon number 5 and this carbon on carbon number 2, this one here. So it means the carbon 3, 4, and 1 are not taking place in the reaction of the ring formation. So it means this this carbon 4 and this carbon 3 are going to remain intact. So what we are going to have is this. I have your carbon 3 there, and then your carbon number 4 there. So this carbon 3 is attached to the carbon 2. Okay, is attached to the carbon 2. So I'm going to write like that, and then I'm going to write carbon 2. So this carbon 2 has oxygen bonded to it like that, and then it has that group again, CH2 and then OH. So that's what it is going to be formed. So this is the carbon 2, and then that is the carbon 1. And then from there, this carbon 4 is attached to this carbon 5. So what is going to happen there is that it's going to go like this. So I'm going to have your carbon 5 there. And then this carbon 5 now, okay, this carbon number 5 now, it's bonded to what? To 2 hydrogens, okay, and then OH. So those hydrogens are going to be this side. Okay, they are going to be this side here. I'm going to write H there and then another H here. And then I'm going to write this OH this side. So I'm going to say O and then H like that. Okay, so that we allow this oxygen here to react with the carbon number 2. Okay, so what we know even from the previous question is that this oxygen here has 2 lone pairs like that on it. Even this oxygen here has 2 lone pairs like that. Okay, so what is going to happen is that this here will be partially negatively charged. And then even this oxygen here will be partially negatively charged because it's more electronegative than this carbon. So it means this carbon is partially positively what? Charged. So these 2 lone pairs of electrons here, they are going to attack this carbon like that to form a bond there. So if they form a bond there, okay, it means these 2 electrons here, they are going to collapse in that bond, okay? And then it means this carbon will have 5 bonds attached. So what will happen is that 2 of the electrons in this, in one of these bonds are going to collapse on the what? The oxygen to make it negatively charged. And then since this one here has lost 2 of its lone pairs, it's going to become positively charged. Okay, so what will happen is this. So I'm going to erase this part. Okay, so those 2 electrons that were on this oxygen have formed a bond now with this carbon. Okay, and then we say that this carbon becomes positively charged. I mean, this oxygen here becomes positively charged because it has lost those 2 pairs of electrons. Okay, and then this one here, the carbon, it now has 5 bonds to it attached. So that cannot happen because carbon can only form a maximum of 4 bonds. So what will happen is that one of these bonds here is going to collapse onto the oxygen. So it's going to have a lone pair there on the oxygen. And because this oxygen has gained a lone pair, it's going to become negatively charged. Okay. And then we come back at this oxygen. What will happen? Okay. What will happen is that this oxygen being more this oxygen here being more electronegative than this hydrogen is going to steal the electrons that are in this bond here. So when it steals the electrons that are in that bond, it means this hydrogen will have less electrons, so it will become positively charged. And then this oxygen here, it has gained 2 of its electrons back, so it will have no charge at all. So I'm going to erase that charge there. So the positive charge goes, and then these bonds break, leaving the hydrogen positive charged like that. Okay, and then that positively charged hydrogen is the one now that comes and attacks this negatively charged what? Oxygen. And then when that happens, okay, when that happens, it means this oxygen will lose one of its lone pairs. Okay, this lone pair here, it will lose it and form a bond with this H plus. Okay, so it means this charge here will go away and you just have OH there. So what you're going to form there is something like this. So I'm going to erase this. Okay. So this hydrogen here will no longer be there. it will be bonded to that oxygen. Okay, so what we are going to have there is that we have OH here with the 2 malone pair there, and then this carbon 2 is also bonded to carbon 1. So this is the ring that we are going to form. Okay, so if you want, you cannot show these lone pairs here, so we can erase these lone pairs there and that. Okay, so this is what we are forming, and then now we just have to insert the other atoms that are attached to this ring. So on carbon number 3 here, what do we have? We have OH on top, and then H down. And then here on carbon number 4, we have OH down, and then H on top. And then this carbon number 5 here, it has HH, and then it is attached to what? To the oxygen. And then this carbon number 2, it has OH, okay? And then it's also attached to the CH2OH group, okay? So we have turned this Fisher projection into a what? Into a ring like that, or into a Haworth projection. So what would be the name of this? This would just be the alpha D, okay, hexolulose, but in ring form. So if you want, you can write the name as hexolulose, okay, because it's in the ring form. But if you want, you just write alpha D hexolulose in ring form. Right, so why is it alpha here? Because the OH there is down. Okay, if this OH is in this position and then this guy is in the position of the OH, it means the OH will be up. That will be what? Beta D hexofuranose. Okay, but this one here, the one that we have written as, it will just be what? Alpha D hexofuranose, or alpha D hexolulose in the ring form. So we've shown the procedure on how to come up with this ring. All right, so I think that's all on question number 3. Okay, we drew this one, we also drew this one. All right, so now let's go to question number 4. So question number 4, they're saying an oligosaccharide is composed of B mannose or beta mannose, okay, alpha glucose, and then beta fructose. The bond between mannose and glucose is a beta 1,2,4 glycosidic bond, okay, and that between glucose and fructose is a 1 alpha to 2 beta glucosidic what bond. Draw the structure of this oligosaccharide and give its systematic name. All right, so the B mannose, it has this structure here that I've drawn here, okay? And then the alpha glucose, it has this structure that I've drawn there, okay? But this beta fructose here, you just don't add it directly here, okay? Because here this is an oligosaccharide, so meaning we're just adding these 3 monosaccharides together, right? Okay, so before you add the fructose here, you have to turn it and invert it, okay? So the original structure for the fructose will be this one here that I've written there in red, okay? So this structure here, you notice that it has carbon 5 there, but here they said the bond between the glucose and the fructose should be 1 alpha to 2 beta. So if I write this structure here directly here, it means the bond that I'll form it will be from 1, okay, to 5 like that, to this 5, I mean. So that is not what we want. Okay, that is not what we want. So it means we have to turn and invert this structure for what? For beta fructose. Okay, so what you need to do is, first of all, turn it 180. So I wrote there that 180 degrees turn. So if you turn it 180 degrees, it means all the bonds that were on the right hand side will start appearing on the left, and then all the bonds that were on the left will appear on the right. So you can see here that these were on the right, but once we turn it, they are on the what? Left. These were on the left. Once we turn it, they are on the what? Right. Okay, so that's what we mean by 180 degrees turn. Okay, so once you do your 180 degrees turn, you are going to end up with a turned beta fructose, which is this guy here. And then after that, you are going to invert. Okay, you are going to invert the atoms at carbon number 2 and carbon number 5. Okay, so notice here that we have this OH on top. So we are going to invert this OH with this group. So this group goes on top, this OH comes down. So you can see here the OH has come down, the CH2OH has gone up. And then even here we also do the inverting. Okay, so this CH2OH has gone up, and then this H now is now down there. I mean, this CH2OH, which was up, it has gone down. And then this H here has gone up there. So that's what we mean by inverting atoms at carbon 2 and carbon number 5. So once you do all that, what you are going to get now, okay, is a turned and inverted B-fructose, which will have the carbon 2 at the position where we want it to be. Okay. Okay. So once you do that now, okay, once you do that now, it means you can write your oligosaccharide. Okay. So what is going to be happening in this oligosaccharide is that this OH here is going to react with an H from the alpha glucose, and that will release a water molecule. Okay, so what is going to remain there is this oxygen here will be bonded to this ring here. Okay, and then here you have this OH reacting with a hydrogen of this turned and inverted B-fructose. So a water molecule is going to be released there. Okay, so now we just have to join whatever will remain there, okay, to form this oligosaccharide. So let's now draw the oligosaccharide that will remain there. So I'm still going to have that, okay, and then we have carbon number 1 there, carbon number 2 there, carbon number 3, and then we have carbon number 4. Okay, let me draw it properly. We have carbon number 4 there, which is bonded to carbon number 5. So carbon number 4 should be there, then carbon number 5. Okay, so on this carbon number 5, we have H, and then C, H2OH, and then there we have HO, and then H, there we have H, and then OH, and then there we have H, and then HO. Okay, and then on this carbon number 1, remember this OH has undergone a reaction, right? So what I have is a bond that is connecting to the other molecule like that. So we have the oxygen here from this from this molecule that will remain. This oxygen here is this oxygen. Okay, so and then I have this tract. So remember at carbon number 1 here, I had this OH that has undergone a reaction. So I'm just remaining with the H there. Okay, and then here this oxygen, okay, is part of this alpha glucose. So what is going to happen there is that you have H there on top. Okay, you have H there on top. I should write it in a straight form. Okay, so you have H here on top like that, and then this here is going to be now the ring for the alpha glucose. So it's going to go, okay, it's going to go like that. We have the oxygen, then that, then that, and then that. Okay, so here we are going to still have the H, and then C, H2OH. Okay, here we are going to have H, and then OH. Then there we're going to have OH, and then H. Okay, and then here there was another reaction. So this OH reacted. So we are just remaining with the H on top there. And then this OH reacted with the what? The hydrogen from the turned and inverted beta fructose. So what we are going to have there is a line joining the oxygen that remained here. Okay, and then another line that goes to the structure for the turned and inverted beta glucose. So what we are going to have there is that on top there, we still have this group. So CH2OH, and then like that, and then like that. Okay, and then we have that, and then that. So this one here, it has the oxygen, and then it's bonded to that guy. So at this carbon number 5, we have CH2OH, and then we have H, okay, and then here we have OH, and then H, then there we have H, and then OH, okay. So this is what we have as our oligosaccharide, Okay, so now the other question there, since we've drawn the oligosaccharide there, the other question was give its systematic name. So its systematic names just comes from the monosaccharide that are making up this oligosaccharide and also the bonds that we can see there. Okay, so its systematic name is going to be, this one here was beta, okay, beta D mano. Okay, so since this is a ring now, we are going to say pura no C. Okay, so beta D pura no C, which is bonded to this alpha glucose by a 1 to 4 glycosidic bond. Okay, and then I'm going to say alpha D gluco. Okay, gluco C. Okay, so the name continues to go, so that's not the right spelling. So pura no C, and then it continues to go. It has okay, let me just write it on top here. So it has hey, where am I going to write this now? Okay, so the name I can erase this. I don't want to erase this structure. Okay, so I'm going to do this. Okay, so the name continues to go. So what we are going to have is okay, what we are going to have is beta D, okay, manopuranosi, 1 to 4 alpha D glucopuranosi, and then this glucopuranosi, which is this guy here, is connected to this beta fructose by a 1 to 2, okay, 1 to 2, and then I have the beta D fructopuronoside. Okay, so it's a long name like that. Okay, it's long. So the name of this oligosaccharide that we've drawn there, okay, its name is beta D, okay, manopuranosi, 1 to 4 alpha D glucopuranosi, 1 to 2 beta D fructofuronoside. Okay, so this here is a furonoside because it is a 5-membered ring. And then these ones here are puronosi because they are 6-membered ring. So that's the name there. Okay, so we are done with this question. We look at question 5, which is the last one. So question 5, okay, we have using a table, list at least 5 functions, which are biomedical uses, okay, of carbohydrates, and for each listed function, mention an example of the carbohydrate with the listed function. All right, so what we are going to do here is just mention the function and then give an example of the carbohydrate that does that function. So the first function is energy storage, okay? I mean energy source, okay? So energy source, so a good example of a carbohydrate which is an energy source is what? Glucose, okay? So glucose is the main energy source for cells in the body, and it is metabolized to produce what? ATP. And then another function is energy storage. So energy storage, a good example is glycogen, okay? So this glycogen, you find it in the liver, okay? It's going to store energy, okay? And breaks it down into glucose for energy when it's needed. Okay, so the extra glucose that you have in your body, it's turned into glycogen and then it is stored. All right, the other function is the structural support. A good example of a carbohydrate for structural support is just the cellulose. So this cellulose is usually found in plant cell walls, and it provides the structural integrity and what? Rigidity. And then another function is cell recognition. Okay, so we have glycoproteins on that plasma membrane there. Okay, we have these glycoproteins. So these carbohydrates are attached to proteins that help cells recognize each other. So we have that as well. So the other function is hormonal regulation. So a good example is insulin. So insulin is also a glycoprotein. Okay, so insulin regulates the glucose levels in the body by promoting glucose uptake in the what? In the cells. So if you have a lot of glucose in your body, okay, this insulin is going to help reduce the levels. And then the other function that I can talk about is protection. Okay, so an example of a carbohydrate that is involved in protection is what we call as the mucopolysaccharides. Okay, so these mucopolysaccharides, they provide lubrication and protection for joints and the organs. All right, so those are some of the functions of the named carbohydrates, okay, in this table here. Right, so we are done with this tutorial sheet. Thank you so much for watching this video. If you'd like to access more videos on tutorial sheets, okay, past papers, test quizzes, okay, be free to register with us. So you can check the procedure on how you can register in the description below there. All right, so until next time, bye-bye.